Hey guys, it's Miss Maneely, and I am going to give you a quick overview of the random variable chapter that we've covered so far. We've only dealt with the first two sections of Chapter 6 on continuous and discrete random variables, and then on transforming and combining random variables. So the third section, which deals with the binomial distribution, we're going to wait until after the semester break. So the first problem on your review deals with being able to identify whether or not a variable is continuous or discrete. Just to remind you the difference between the two, a discrete random variable, there are two criteria. In order for it to be discrete, it has to be a finite set of values, or a finite set of distinct values. And that would be a discrete random variable. Often with a discrete random variable, you can count them. So there's countable outcomes. Oops, I'm writing it twice. There's countable outcomes. With a continuous random variable, there's an infinite, it's an infinite set. The outcomes are measurable. And just to give you some of the same examples that we've looked at so far, discrete would be something like the number of students in a room, the number of desks in a classroom. Continuous would be like the amount of gasoline in my car, or the amount of water being drained from a bathtub. You can't count water, you can't count gasoline. So those would be continuous variables. So letter A says the number of cars in a parking lot. We can assume that there are a fixed number of spaces, and so there would be a finite number of cars that could fit. Obviously, we can count them, so this would be a discrete random variable. So it's pretty obvious, I think. Income of Maryland state employees. Well, if you think of income as being rounded to the nearest cent, then it makes sense that you can count the income. You know, $25,362.25, and then you'd have 26 cents, and then 27 cents. The problem is there really isn't a cap to how much a state employee could earn. And so it really isn't a finite set of values. And even if it were, it makes a little bit more sense to treat it as a continuous random variable. So a lot of times with things like salaries and income, even though you could look at it as a discrete random variable, we're going to treat it as continuous. In letter C, the winnings after playing the slots 3 times, that kind of gives you an indication that there's a limit to how much you can win. And again, we could count it at this point, and so it would make more sense to consider this to be discrete. The number of songs that Paul can download in a given hour, the fact that there's a limit to how long he's downloading these songs, there would be a limit to how many songs he could download. We could certainly count them. So this, again, would be discrete. And then finally, the length of a movie in minutes. There really isn't a cap to how long a movie can be. And so similar to the income situation, I mean, you could certainly count the number of minutes, but if there isn't a limit to how long a movie can be, if there's not a cap, then it's not finite. It would be considered infinite. And so again, it makes more sense to treat this as continuous, even though you might be able to argue that you could think of it as discrete. It makes more sense to treat this as a continuous random variable. Okay, and number 2, it says in an experiment, I think we saw this in one of our homework problems, in an experiment on behavior of young children, each subject is placed in an area with 5 toys. The response of interest is the number of toys that the child plays with. Past experiments with many subjects has shown that the probability distribution of X, or the number is going to equal the number of toys the child plays with, is given by the following table. So obviously this is considered a discrete random variable. We can see that there are a distinct number of outcomes, and it's limited to 5. So a child can play with between 0 and 5. In order for this to be a legitimate probability distribution, each of the individual probabilities has to be between 0 and 1, and the sum of the probabilities has to equal 1. And that means that the probability that a child plays with 4 toys is going to be 17%. And all I did is add the values in the table and subtracted them from 1. So the probabilities that you're asked to calculate, make sure, again, that you're using proper notation. And now that we've moved on to using random variables, it's going to be important that you use the numeric notation. So instead of, you know, writing it like this, child plays with 4 toys, we actually want to quantify that in terms of our x variable. Since we've defined the variable x, we would say the probability that x equals 4 is 0.17. In part B, where it says a child plays with at least 3 toys, at least means 3 toys or more. So that's going to be x is greater than or equal to 3. And remember, with the discrete random variable, there's a distinction between equals or greater than or equal to and just greater than. With the continuous random variable, there wasn't a distinction between those two inequalities. But this time, I would just simply add the 23% to the 17% to the 11%, and that gives us 51%. In letter C, a child plays with no more than 2 toys. That means that it's 2 toys or less, and so this is going to be the probability that x is less than or equal to 2, and so that's going to be 0.03 plus 0.16 plus 0.3. Remember, when we list our probability distribution, when we enumerate all the different outcomes for x, they are distinct. That also means that they are discrete, so that there's no overlap. I can simply add the probabilities together. I don't have to subtract the intersection because there is no intersection. They're all disjoint. And so I think that is 49%. And then in part D, it says to calculate and interpret. And so we're looking for the probability that x equals 1 or x equals 2. So that's going to be 16 plus 0.3, which is going to give us 46%. And so basically we're saying, I'm not going to write this down, that there's a probability of 46% that a child plays with either 1 or 2 toys. In letter E, and I think on your paper I might have misnumbered it, we're looking at the probability that x is less than 2 or greater than or equal to 3. The only outcome that's not included is the probability that x equals 2. So this you could also just find as 1 minus the probability that x equals 2. Might be easier to look at it that way. So 1 minus 0.3 is 0.7. The other alternative would simply be to add 0, 1, 3, 4, and 5. And if you add them all together, you get 70%. And basically what that means is a child doesn't play with 2 toys. So, or you could look at it as the child plays with 0, 1, 3, 4, or 5 toys. Letter F is asking us to calculate the mean, and G is asking us to calculate the standard deviation. You do not have to go through the long process here. You can simply use the lists on your calculator to do this. And so, whoops, it's not clearing. So I would enter in 0, 1, 2, 3, 4, and 5. And then in my list 2, I'd enter all the probabilities, which is 0.03, 0.16, 0.3, 0.23, 0.17, and 0.11. Okay, and so I have all my outcomes in list 1, the probabilities or the relative frequency in list 2. If I go to stat calc, I'm only dealing with one variable. I'm dealing with x represents the number of toys that are played with. So I'm going to use list 1, but I have to take into account that the number of toys that are played with is not distributed evenly. So I have to take into account the frequency or the relative frequency, which is the probability in this case. And that is in list 2. So the calculator will weigh each of those outcomes to give me a mean, and I expect you to use the correct notation, which would be mu of x, or you could write it as e of x, because that's expected value. And that is 2.68. And again, you want to make sure with mean and standard deviation that you use the appropriate units. And so we're talking about toys. The standard deviation is going to be 1.311. Okay, and again, I do expect you to round to 2 decimal places, or to 3 decimal places. And again, don't forget your units, because the units are going to be built into the problem. So if you forget to label with units, you'll lose a point. And I know that's really frustrating for you guys. Okay, in number 3, it says from past years, Alex believes she will get a $100 birthday check from her grandmother with a likelihood of 40%. She also anticipates she has a 60% chance of getting a $50 bonus from her boss. She believes she has a 20% chance of getting both the check and the bonus. So if X represents the random variable or the amount of money she receives, we want to give the probability distribution. So it's not quite as simple as you might think it is, because if I think about my X as being the amount of money she receives and P of X is the probability, I know that she can get $100 from her grandmother. I know she can get a $50 bonus. I know she could get both, but I also know that she might not get anything. And if I simply list the values as they appear in my problem, we know that she has a 40% chance of getting the $100, a 60% chance of getting the bonus, 20% chance of getting both. Right there, those probabilities add up to 1.2, which is too much, obviously. Your probability distribution must have a sum of 1. So there's an error here. We have to kind of think about this problem in a different way. And you're given a hint, and the hint is to use a Venn diagram. I will tell you right now that I'm not going to put that hint on the test. So you're going to need to recognize that the probabilities are too big. And so we're going to have to construct a Venn diagram. So here's the $100, here's the 50, and in the middle will be the 150. And then obviously out here, she's not earning anything. So we know that, let's start where the overlap is. We know there's a 20% chance of getting both. So if she's got a 40% chance of getting $100, that's this whole circle. So if 20% is included in her getting both, that means that she's got a 20% chance of getting $100 only. And then we know she has a 60% chance of getting the $50 bonus. Again, I have to subtract out the overlap, which leaves us with 40% there. So altogether, that adds up to 80%, leaving us with a 20% chance that she gets neither. Now I can complete my probability distribution. 20% chance of getting $100, 40% chance of getting 50, 20% chance of getting 150, and a 2% chance, or 20% chance of getting nothing. With the money that she receives, she's hoping to attend a concert with her friends. The tickets cost $85. If Alex has no other financial resources, should she expect to go to the concert with her friends? So as soon as you see this word expect, we're thinking about the expected value. How much should she expect overall from this distribution? Remember, expected value is the same thing as the mean. So what I want to do is figure out the mean or the expected value of x. And again, you're going to do it with the same process on your calculator, or you can simply take 100 times 0.2 plus 50 times 0.4, because you don't have to find the standard deviation for this problem, plus 150 times 20%. And then obviously you don't really have to add the 0, but just to complete it, I'll put the 0 in there. And so we know that the expected value is actually $70. And since the expected value of her receipts, so since the expected receipts is $70, it's not enough for her to pay for a concert ticket. And therefore, she should not expect to go. All right. In number 4, it says that let x represent a random number between 50 and 70. So it asks if x is discrete or continuous. Well, if it's any random number between 50 and 70, that means it could be 50.1, 50.11, 50.000001. So it's considered continuous, even though there's a cap. There's an infinite number of values that are between 50 and 70. So this is a continuous random variable. And it says to construct a density curve to represent the distribution. So if I'm dealing with x, remember when I do a density curve, my random variable is going to go on the x-axis, and the probability is, or the relative frequency, is my y-axis. So if I'm thinking about a number line, and I'm thinking that x can be anywhere from 50 to 70, I'm going to ask myself, are any of those outcomes more likely than the other? Obviously the answer is no. This is what we call a uniform distribution. That's a 70. And so it's basically going to look like a rectangle. Sorry, I overshot that. And so the next question would be, well, how tall is the rectangle? I know how long it is, but what's the width or what's the height? And so what you have to remember is that all density curves have an area that's equal to 1, and that corresponds to the sum of all the probabilities, because all the sum of the probabilities has to add up to 1. And so if I'm trying to figure out the height of my rectangle here, you know that area is equal to length times width. If I know my area is 1 and I know my length from 50 to 70 is just 20, if I solve for the width or the height, whatever you want to call it, I get that that's going to be 1 over 20. So I know this value here is 1 over 20, or 0.05 if you want to look at it that way. And so if I'm looking for the following probabilities, now that I'm dealing with a continuous distribution, there is no distinction between a greater than and a greater than or equal to. Because the probability that x equals any particular outcome is simply going to be 0. So for number 3, I know that's just 0. So it doesn't matter if there's an equal sign or not. So if I'm trying to find the probability that x is less than 55, I'm basically just trying to find the area of that rectangle, which is going to be 5 times 0.05, or 25%. In the second one, we're looking for the probability that x is between 53 and 57. So that's just going to be 4 times 0.05, which is 0.20, or 20%. Greater than or equal to 62, that gives me a width of 8 and a height of 0.05, which is going to be 0.4. Less than 60 or greater than 65 is going to be 10 times 0.05 plus 5 times 0.05. And that gives me 0.75. And then lastly, we're looking at x between 51 and 54. That's going to be 3 times 0.05. If it's an or, we know there's no overlap. X is greater than 61 is going to be 9 times 0.05. And that is 0.6. Number 5 is similar, except this time you're given the graph, and we've done probabilities like this before. This is, again, a continuous random variable. I didn't label this, but that would be x, and that would be p of x. And so if I'm going to try to find these probabilities, I have to first think about what the area of each of these little rectangles are. So I already know that the total area has to be 1, and so if this is set up properly, they should all add up to 1. And so if I think about this particular block, I know it's 1 wide and 0.1 high, so the area is 0.1. That means that this area is 0.1. And I know that together, this area must also be 0.1, because if I add 1, 2, 3, 4, 5, 6, 7, 8, 9, this area is also 0.1. And I'm not sure if you'll need to break it down further. We'll look at the problems to see. But if we did, we would just find probably the area of this little triangle and then subtract it from 0.1. So in letter A, it's asking us to find the probability that x is between 0 and 3. And remember, the equal sign doesn't matter. So I'm simply going to add up how many, I'm going to add up all those 0.1s. And it looks like there's 8 of them. So it's going to be 0.8. For part B, we're looking at the area between 2 and 3. So that's this area here. That's going to be 0.2. Probability that x equals 2, again, this is a excuse me, a continuous random variable, so the area of a line is just 0. The probability that x is less than 2, so that's this rectangle right here. If I add them up, that's going to give me 0.6. And greater than 3, and there's 2 blocks that fill that up, so that's going to be 0.2. In number 6, it says a packing machine is set to fill a cardboard box with a mean of 16.1 ounces of cereal. Suppose the amounts per box form a normal distribution with a standard deviation equal to 0.4 ounces. What's the probability that a randomly chosen box is at least 1 pound or 16 ounces of cereal? So if we let x represent the amount of cereal in the box, or the number of ounces, we're told that x is a normal distribution and it has a mean of 16.1 and a standard deviation of 0.4. And in part A, I'm just finding the probability that x is greater than 16 ounces. Okay, and so the first thing I need to do is rewrite that in terms of my z-score. So I'm going to do 16 minus 16.1, and I'm going to divide that by 0.4. And I get negative 0.25. So I'm looking now for the probability that z is greater than negative 0.25. And now I'm going to go to my distribution menu. Remember, we're always choosing normal CDF, and my lower bound is negative 0.25. My upper bound is positive 999. It's infinity. And let's see, my mean in this case, since I've standardized it, I want to make sure I'm using 0 and 1 as my standard deviation. And I get 0.5987. And remember, when you're dealing with a normal curve, I do expect you to write your probability in terms of your random variable x. I expect to see that you've standardized it, and then I expect to see the probability. So that each of these will be worth 3 points. Part B, what's the probability that a randomly chosen box has less than 15.9 ounces? the sake of time, I'm just going to go ahead and tell you that when you standardize it, it's negative 0.5. So we're looking for the probability that z is less than negative 0.5, and that should be 0.3885. And then in part C, you're looking for the randomly selected box weighing between 15.95 and 16.13. And when you standardize those values, it's negative 0.375 is less than z is less than 0.075. And I just realized on my key that I called this x, so if you're looking at what I printed online, I wrote that wrong. This should be a z. Okay, and so this time, this is your lower bound and this is your upper bound, and then the area between is 17.61. Now in letter D, it says, suppose the store is running a buy one, get one free promotion. Let X represent the variable, let the random variable T represent the amount of cereal in the two boxes. Now determine the mean and the standard deviation of T. So remember, T is going to equal, I don't want to say 2x, I want to say x plus x. And if you want to distinguish between the two cereal boxes, you can give a subscript. And the reason I want to think of it this way is because they are two independent random variables. It's not going to make so much of a difference with the mean, but when I'm trying to find the standard deviation of the two boxes, it's going to make a difference in the formula that I use. So to find the mean of T, obviously, I'm just going to add the two means, the 16.1 plus 16.1, and I get 32.2 ounces. Oops. Okay, to get the standard deviation, I have to work with the variance. And so the variance of T is going to be the sum of the variances. Well, the variance for one box is 0.4 squared. And to be honest, I didn't even find the sum. I just went ahead and said that the standard deviation is going to be the square root of that. And ultimately, the standard deviation becomes 0.5657. And again, that's in ounces. You always want to make sure you use units for mean and standard deviation. The variance does not have a unit. Letter E is now asking, what is the probability that the two randomly selected boxes contains less than 32 ounces of cereal? So now that I've put the two boxes together, I've got to think about how T is distributed. Well, since the individual boxes are distributed normally, I know that when I put them together, T will also be distributed normally. The mean for this new distribution is going to be 32.2, and the standard deviation is going to be that 0.5657. So if I want to find the probability that the two boxes, this time I'm calling it T, is less than 32, again, I'm going to standardize. And when I do, I get the probability that Z, and again, I made an error on my answer key. I was doing this really fast. That should be a Z, is less than negative 0.3536. And then again, if you use the calculator, you should get 0.3618 as your probability. Okay. In number 7, this is a little tricky. It's almost like a puzzle. It says, following are parts of a probability distributions for the random variables x and y. It says, if x and y are independent, then the joint probability, where x equals 1 and y equals 2. So even though you don't see the and, a joint probability means that it's and. So if the probability of x equal 1 and y equals 2 is 0.1, then what is the probability that x equals 4? And just remember that joint probability is the same as an and statement. So the first thing I'm going to look at is there anything that I can figure out without having to do much in terms of the information that's provided. So if I look at my distribution of y, I can see that there's only one probability missing. And since I know that those probabilities have to add up to 1, I know that the probability that y equals 2 must be 0.5. Because if the probability that it equals 1 and 3 is 0.4 and 0.1, together that's 0.5. So the probability that y equals 2 must be 0.5. I can't really narrow down anything with x because I have two things that are missing. So now I'm going to use this piece of information. I'm told that the probability that x equals 1 and y equals 2 is equal to 0.1. Now we're told that they're independent. So you have to remember your probability rule here. If it's an and statement and I know they're independent, this is the same thing as the probability that x equals 1 times the probability that y equals 2. And so I know that's 0.1. Well, I also figured out that the probability that y equals 2 is 0.5. So that leaves me to this. The probability that x equals 1 times 0.5 is equal to 0.1. So if I want to determine the probability that x equals 1, I'm just going to divide both sides by 0.5. So the probability that x equals 1 is 0.1 divided by 0.5 is going to be 0.2. And so now I can go up into my table and I know that the probability that x equals 1 is now 0.2. And if I want to find the probability that x equals 4, it's just going to be 1 minus 0.2 minus 0.2 minus 0.3, which I think leaves me with 0.3. And so that's how you do it. So it's kind of like a puzzle. I actually really like this problem, and I do think that there's one of these on your midterm. So you might want to just put a big star. There's definitely going to be one. Okay, we have one more problem. I'm going to try to do it before school starts. We're given two random variables, x and y. We're told that they're independent. We're told that the mean of x is 10, the standard deviation of x is 3. That means that the variance for x is going to be 9. We're told the mean of y is 15, the standard deviation for y is 6. That means that the variance for y is going to be, I'm sorry, the standard deviation of y is 4. When I square that, that's going to be 16. Okay, so if I want to find the mean of x plus y, remember with means, it's just very straightforward. I'm going to do 10 plus 15, and that gives me a mean of 25. If I want to find the variances, I'm simply going to add the two variances. So we've got 9 plus 16, and that gives me 25. The standard deviation is going to be the square root of that, which is 5. Okay, for the next one, we've got 3x minus 2y. Again, we're going to do the same thing to the mean. So that's just going to be 3 times 10 minus 2 times 15, and that gives us 0 as the new mean. The variance, remember, we never subtract the variance. We always add. And when I'm multiplying by a constant, I have to square it first. So that's going to be 3 squared times 9, plus, and think about it, negative 2 when I square it is going to end up being a 4, positive 4 anyway. But it's going to be plus 2 squared times 16, and that's going to give me 145. To get the standard deviation, I take the square root of that, and I get 12.042. If I'm looking at 3 minus 2x, to do my mean, it's just going to be 3 minus 2 times the mean of x, which is 10, and I get a negative 17. When I do the standard deviation, remember with the variance, adding and subtracting is not going to affect the spread at all, so I'm just going to ignore the 3. When I square that negative 2, actually it's always going to be a positive 2, so it's going to be 2 squared times 9, and that's going to give me 36. When I take the square root of 36, I get a standard deviation of 6. And then 4y minus 2, that's just going to be 4 times 15 minus 2, and that gives me a mean of 58. The variances, again, I'm going to square that 4 times the 16. Subtracting 2 is not going to affect the spread. And when I take the square root of 256, I get 16. So there are a couple that I think kind of go against what you might expect, and that would be the variance and standard deviations for these two. Because you're always adding when it comes to variance and standard deviation. Okay, I hope this review was helpful. Make sure if you have any questions that you're prepared with them when you walk in the door so that we can take the quiz right away or the test right away and then start working on the midterm review packet.